Good morning and good evening and all that fun stuff to everybody who's joining today. We are joined by Robert and Tyler, who I don't think need any sort of introduction. You've seen them before in the Delta community a little bit, that's fine. If you guys want to say hellos as well, we can do all of that. Today's episode, we're going to be talking a lot about where Delta Rust came from, what the kernel project is, and why that's actually, helping to make Delta Rust an even cooler project. So with that, I can turn it over to Robert and Tyler. If you guys want to say good morning or good evening or anything, feel free. So
I'll say good morning because it's morning in my time zone.
I'll say
the west coast of the US.
I'll say good evening because it's approaching evening in my time zone, which is also the west coast, but of Europe. Yeah.
Awesome. Cheers.
I'm gonna eat my breakfast while we talk too.
Wonderful. This is excellent. So today we're going to talk a little bit about kind of early fragmentation within the Delta project itself and how the kernel came to be. So Robert or Tyler, either of you, if you want to kick off and kind of talk about even just the genesis of the Delta Rust project.
Robert, if you'll let me jump in at the beginning. So when I first got involved in the Delta project, there was just Delta Spark. There's one implementation. There was just that. And this was about five or 6 years ago. The time's a little fuzzy to me. QP Howe and I created the Delta Rust project. And in the next couple of years, in that 2020 to 2021 timeframe, a number of different implementations of the Delta protocol sprang up. Because suddenly Delta became, extremely useful. It became widely adopted by a number of different organizations, to where we saw implementations in Go, some implementations in C, C++, some implementations hiding in proprietary systems like Azure Synapse or other things like that. And so in, 2022 or 23, again, time flies, we looked out at the ecosystem, and it was a bunch of completely different implementations of the same foundational protocol. And so we had this really big challenge of well, what version of Delta are you, not necessarily what version of the protocol, but what implementation of Delta are you using to do that, this or the other thing? And that's what sort of originally led us to implement or start working on kernel. And with that, I'll pass it to you, Robert, to tell us a little bit more about it.
Yeah, certainly. As you just mentioned, actually, version or implementation or feature of Delta is already an interesting thing. I think a lot of these pain points were kind of already captured in the community, and not necessarily exclusive to open table formats, right? I think these were pain points felt kind of across projects, across data systems in general. And Carly, we do have a couple of slides that will kind of be loosely following to guide our conversation a little bit. But we will not stick to it too religiously. But the composable data systems, or composable open table formats in Delta RS is kind of what we named this here. And this is based on two bigger trends. There is the open lakehouse. I think if you're interested in Delta, you probably heard the term lakehouse before. Lakehouse being largely driven or fueled by open table formats. Open table formats allowed the kind of transactions against the table, like all the asset guarantees that you know and love from a warehouse, but also allows much more kind of performant queries on all of this. And maybe in parallel, the composable systems movement started. I don't know who founded it. There is a movement. Yeah.
Oh, man.
I mean, a lot of this, we come from Rust, right? And I feel like Rust has cultish tendencies.
Does it?
The movement. I'll have to get the flag ready. Composable systems. I mean, what's interesting about the composable systems thing is I think we're like, there's this sort of circular nature in the technology industry sometimes where we're sort of relearning lessons of years past, but at a different scale. So like the original discussion around object-oriented programming with Smalltalk and some of that composability with Smalltalk, we learned on a single machine. And then in maybe the last 10, 15 years, we're starting to realize that these distributed systems, there's also composable pieces of these distributed systems that we also need to sort of define discrete boundaries around and encapsulate and build up and out with. And so like, if you were to come to this slide, like say 10 years ago, you could be talking about building, you know, a client-side web application. You could be talking about building a, you know, a server-side Rails application, like all sorts of things sort of fit into this world of like, we need to compose these different blocks in order to build the big monolith of thing that we're trying to solve for.
Absolutely. And I think composable systems, just as you say, they're doing the same thing just on a separate scale. And Arrow is kind of the poster child of composable systems in a way, and also underlines this quite nicely, right? I mean, there is means of communicating data between system boundaries. I don't know, use JSON serialization, use whatever you want. But with data systems, it became infeasible to pay the price to just take, okay, I have my huge record batch, I don't know, the gigabyte of data I keep in memory and process on, and now I'll just kind of serialize this to JSON really quick, make it all strings, and have the other side parse all of that stuff again. So that was
real quick and easy.
Exactly. So, and a lot of these components contain a lot of optimizations, and Arrow is a very good example of this, right? The in-memory representation of Arrow, of data with Arrow is highly optimized. So what we really want is, we want the same thing for table formats, but as we'll see in a second, there are maybe some challenges. And I just love this quote. This is from the README of Nimble. For those of you who don't know, Nimble is kind of a project driven by Meta that aims to have kind of, let's say, I don't want to replacement and evolution for Parquet. So it's a file format. But the statement they make literally kind of at the top of their README, and I'll just read this out loud for everyone really quick. We strongly discourage developers to re-implement Nimble spec to prevent environmental fragmentation issues observed with similar projects in the past. Delta is a great example.
Meta voice.
Yes. Yeah, we all know those pains across various projects, and composable systems aim to address some of this, right? They aim to say, okay, here there is this little piece, like understanding a Parquet format, understanding what have you, that you can just kind of plug into your other systems. And again, going back to Arrow, Arrow would be a good example. You could isolate Parquet reading, and the thing that you give back is Arrow as the agreed upon representation for data for exchange. Right, so that allows you to come to put this into a component and share this. So open table formats, I think we talked about this at length, but the open lakehouse is really powered by the open table formats, and composable systems is essentially this train. We take a data system. Tyler, you mentioned the monolith before. I think somewhere in the paper it says, okay, look at the investments in database startups a couple of years ago, and all of those seed rounds today that may not sound much were kind of in the couple of $100 million. so sort of maybe not seed rounds, but Series A, because it's incredibly exactly today. It's like, well, but the reason for this was you needed to build a monolith, and building a performant data system end to end is just kind of literally decades of engineering hours you need to invest in that. But composable systems kind of switch the storyline and say, okay, you can take all of these components, and by now, again, Parquet being a great example, Tyler loves how much I like data fusion and how much I try to shove it in there. But this is a great example. Parquet reading in data fusion is very advanced. Very, very advanced. Uses a lot of tricks, a lot of optimizations, that you can get sort of off the shelf in the open source right now, which, I don't know, 10 years ago, building just the Parquet reading in Data Fusion would need a team of experts putting in some serious engineering hours, right? So deconstructing these systems and just customizing the pieces you're actually interested in. Maybe the experience, maybe you have a very powerful query language that you want to then parse into plans, or I don't know, whatever you're really good at, you can just kind of replace that one piece of the entire architecture. But again, open table formats kind of eluded that for a while, and there's reasons for this. The reason is open table formats kind of span multiple layers in this mental model. Again, we mentioned Arrow, but not every engine uses Arrow. So if you want to be usable by multiple engines, DuckDB being a good example, is very compatible with Arrow, don't get me wrong, but internally it doesn't use Arrow. They have their own representation with kind of a feature, for instance, that Arrow doesn't have, which is selection vectors. So they can actually filter a batch of data without copying it, which you can't do with Arrow. You actually need to create a copy. But they can do stuff like this. And it also kind of passes the boundary between the storage layer and the execution engine. So you need to access the storage, and the traditional approach would be, I don't know, give me a file system implementation. But give me a file system implementation implies that I'm doing the Parquet reading, I'm doing the JSON parsing, I'm doing all of this, which an engine may have very advanced, sophisticated, optimized implementations for. So how do we go about this? Well, this is again just highlighting the. Go ahead, Tyler.
I was gonna say, your assessment is correct. I think there's one thing that should be said. Part of the reason why open table formats were built the way that they're built is because their goal was to solve some business problem. Like Delta was created to solve very specific problems. Iceberg was created to solve very specific problems. Only it's sort of we do have a little bit of like the second system challenge that gets talked about in the Mythical Man Month, in that we've built a system, it works, it solves the problems, and now we've got to go figure out how to improve upon that. And it can be tempting to rebuild it from scratch. And there's a couple of projects that I've seen that are like, that have looked at what Delta has and what Iceberg has and says, okay, but we can do better. And so they start from the, try to build that entire stack. And what's I think novel about what we've been attempting over the last couple of years with Kernel to do is there are some discrete lines. Like you drew lines around these in the previous slide. There are some discrete lines where we know that there's this part that needs to be composable, reusable in some fashion. And there's other parts that aren't, that are very specific to what you would do in Delta Spark, what you might do in a writer operation, like some of the Kafka Delta ingest or something like that. And so there's different pieces of the puzzle that not every implementation needs. But at the beginning, Delta was created for Spark. Like Iceberg was created, I think Netflix, Scott, you might remember that better than I do.
And with Spark as well for that.
And with Spark, like there was a very specific mindset around the end-to-end system that these things were going to solve for. And they've sort of like become, through their own success, needing more of this composability. I think it's actually very difficult for any system to build in a modular composable way from the beginning and meet the business or organization goal that you're actually trying to meet. Like it's galaxy brain level thinking that you have to have in order to do that from the start.
So would you also say that a lot of the fragmentation occurred because of the success of the project, as people wanted to connect to be able to essentially have like an interop like layer to be able to read something that was say created with Spark or created with Delta Rust within their own ecosystem. So if you think about Trino, or if you think about DuckDB, right? Like I can write somewhere else, and as long as it's interoperable and I'm following the protocol and protocol or specification correctly, then I should, in theory, be able to read. And a lot of times that's also where the problems come from. It's like, well, I wrote it with system X, and now system Y doesn't allow me to read what's going on. And everyone starts to do like the finger pointing and like that blame game, when it's like, well, it's like, it's like, I'm not going to touch that one, but it's so that's pretty much the catalyst for a lot of like the kernel operations, where, kernel can then be given to the engine developers to make everything interoperable without as much effort.
Mhm.
Yeah.
I think
And
the Delta as an interop layer is a really important point. Like I've seen that with a number of different organizations where you sort of treat storage as your like Delta table layer as where every system is either pushing data into or fishing data out of. And so there's a lot of data pipelines that I've seen in the last few years where rather than having, I think it was called the Lambda architecture, I'm not sure, but like spitting data into Kafka, processing it, spitting it into another topic. Instead of doing that, just going into Delta and then having something else fish out of Delta. It's a pretty, I would say, maybe not simple, but it's a pretty straightforward way to bring all of these different systems to the same sort of like data ecosystem, which I think is why we have seen this sort of like explosion of client implementations, is because everybody wants to come drink from the same river, and they've got to build something to get there. That might be too many water metaphors.
No, it's it's good. I think the water metaphors are good too. I think it's interesting when you're talking about like the Lambda architectures, because a lot of this stuff came off with like there's like the Kappa architecture where it's like kind of, I'm going to go fast, I'm going to go slow, because fast is usually problematic. And so I'm going to always be like, it's real time, and then we're going to go and fix it later. And there's also like the SMAC pattern from back in the day, where it was like Scala, Mesos. I can't remember what else the other thing is, Cassandra and Kafka. And then a lot of that was required to be able to, query your data while it's like in flight and anything else like that. And now you have systems where it's like, well, I can just read or stream from the same, underlying, protocol
go to Delta
specification.
Go to iceberg.
Yeah. And then reduces all that complexity as well. So, you have that, you do have that. Yeah. You go, Robert.
Interestingly enough, I think kind of the ideas behind composable systems also created the need for composable systems. What do I mean by that? Is back when those table formats were invented, you could say, I think, Spark reigned supreme, right? There was very little competition compared to today at that point, and a lot less heterogeneity in kind of the client, the query engine implementations out there. This has changed also, and this is what I meant, kind of created its own problem, because today it's much more feasible for much more teams to actually build a query engine, building on some of the components out there and just kind of customizing what they want for it. And also the point you already mentioned, not only like the table formats have also become the interchange format between vendors, right? So if you want to move from BigQuery to Snowflake to Databricks, usually the way this goes is you have your data in Iceberg or in Delta, and then have those different query engines operate on all that stuff, right? And this just exemplified, accelerated the already existing kind of fragmentation issues that we've seen. All right, I think we talked a little bit about why this is good, why people need this. Maybe just highlighting some points, and I may have involved in some of the situations that got a little risky. But if you have this multi-writer scenarios, multiple implementations, and you extend trust to those implementations in a sense of, yeah, they'll probably behave in that they'll probably not corrupt my data, hopefully, fingers crossed. But ultimately now each implementation needs to be correct. And that was a challenge in the very beginning when we were at version 1 or 2 of Delta or what have you. But as features get more complex, there's more room for error in there also, right?
It's not about being correct. This is a point that has come up for the Delta RS ecosystem time and time again. It doesn't matter what correct actually is, because that's not the real world that anybody lives in. It has to be consistent. Mm-hmm. And so it actually doesn't matter what the Delta protocol says. It does, but like in a lot of cases, it doesn't matter what it says when you've got an actual table that was written by an engine that you can't read by another engine, right? Like it's the consistency across the ecosystem to where if there's a bug, we should all kind of have the same bug. Or if there's, an interpretation of stats as this versus that, or a time zone, it means this versus that. It's the consistency that I think is the key. because I mean, Robert and I have contributed a lot of code to Delta RS, which is like not protocol compliant. It's not actually what Delta is, but we know that there's tables in the real world that have data that's shaped like this. And so we want to make sure that we can read that, you know? And so it's the consistency thing that I think is the most important part about kernel, is that we're consistent.
Would you also say that, like, so if you think about the protocol and you think about like the specifications in general, right? There's what's written on paper, as you were talking about before, what's formally been documented, and then there's what occurs outside of documentation as well. And we all know that documentation is not always up to date. Protocols are not always up to date. And so I think it's good to talk about this in terms of, like, you know, it's real world expectations for consistency versus just correctness to specification as well.
And exactly to that point, I mean, I picked the nimble quote because the other one was in a personal talk, but I talked to Hannes from DuckDB once, who well wrote much of DuckDB, but also wrote the Parquet implementation. And sort of kind of in my own interpretation, something he said was, if you're implementing a Parquet reader, you're not implementing the Parquet spec, but you're essentially implementing against all the weird bugs out there. And he has this like huge collection of various Parquet files he collected in the wild that ideally you would be able to read, even though they may not be technically compliant.
So if you want to go on like some fun open source archaeology adventures, think about what powers the World Wide Web. HTTP. HTTP is very well specified. I don't necessarily agree with some of the decisions made in those specifications, but it's very well specified. And then go look at what Daniel Steinberg with curl has done, and all of the flavors of reality of what HTTP, as spoken by different servers over the last 40, 50, many years, what that actually has been, right? So like when we talk about consistency, it's the consistency as like a lived reality, as opposed to what's documented, as you were alluding to, Scott. Because even if everybody has the same sort of compliance suite, like the CNCF has like an OCI compliance sort of spec, there's still variations because you can't get everything into a compliance specification. You can't, like, it's just not possible. And so the more we're able to share actual code, the more that we actually are using the same building blocks between these different systems, the more likely we are to have like consistent execution, consistent behaviors, things like that.
Yep. Which I think is a good segue back to composable systems.
Yes. So let's dive deeper into those. So, and I'll run through this really quickly. But this is essentially just saying this isn't sort of a figment of someone's imagination, but this actually works. And we've seen this work out really well in Delta RS. And here again, we're talking about composability in general. We'll get to composability for kernel specifically just in a little bit. But yeah, this is just sort of a quick plug for the Delta Lake 1.0 bindings, where many things landed.
We did a lot.
Yes, many great things landed. Not all of them related to composability. Also, if you look at the lazy readers, the streamed executions, a lot of this was embracing Arrow and embracing some of the lower level Arrow abstractions. This is a little bit what it looks like. So Parquet JSON reading, this is from Delta, from RS. We have the Delta RS engine, which kind of negotiates between Data Fusion and Parquet. And this is a simplified view because, Tyler, you mentioned Delta Kafka ingest, which, for instance, does not depend on the Data Fusion crate as such. So there is an Arrow-only version of some of this. And then there is sort of this PyO3, Arrow3. I don't think we need to go into the details of what these individual technologies are, but there is sort of a mapping into that stack. And here, this is just a little bit of code. Some popular engines, Daft, Polars, PyArrow, are involved, and we try to exchange data between those engines. And one thing to note is within Delta RS, there is no Daft specific code. There is some Polar specific code because of offsets, but very, very little. None of them tell Polars how to read Delta or need to transform data or anything. Same for Pyro. We used to have a Pyro engine that's been deprecated. Right now it's all Rust. But if you look at especially the lower lines, here we're moving data between all of these engines. And the interesting part is, if you look at this, let's not dive into why we consume 100 megabytes in the beginning, but this is essentially just kind of a very naive memory profiling using some example data from the well-known yellow cab data set. And you need to know that this is sort of timed. I think every 2 seconds, like in the actual testing script, in order to discern when what happens, and it's local to also have like a little bit of stretch on the time axis. About every two, so there's like a pause of every 2 seconds between loading this, right? So initially we consume our lazy stream once. That was one of the features mentioned in Delta 1.0. So everything is lazy, and then bum, we move between engines. We're not going to go into resident and heap size and all of this unless Tyler wants to kind of detail this out a little bit. But what we see in this plot is that moving data between all of those engines doesn't consume additional memory. Sort of the heap size is more of an, okay, I may need some, but it's not yet populated or filled with data. So we're more looking at the blue line here.
So I think the important detail is, I don't know that I've seen somebody using Daft and Polars at the same time. Like, hopefully people aren't getting too esoteric with their Python data processing stuff. But from the Delta RS perspective, like, we are able to support n number of engines sitting on top of us because we have that composable interface of Arrow interchange. And Arrow, and we're talking about Apache Arrow, which is arrow.apache.org. Fantastic project, fantastic format. Mm-hmm. But a lot of the work that's gone into the Arrow ecosystem, we are building on top of to make this possible.
Yeah,
it's really, really cool. But the nice thing about what you're showing there is improvements that we make in Delta RS on reducing memory consumption or the laziness has this effect where it works for everybody that's sitting on top. Okay? And that's sort of the world that we're pushing more and more towards is, you know, performance improvements below are just benefiting everything up top. So it's not narrow, you know, specific use case types of performance improvements.
Real quick, just for anybody who's not familiar with laziness in the way that we're talking about laziness right now, do you want to talk about like being aggressive or waiting to consume memory? I don't know who wants to take.
So when you create a Delta table, there is some I/O going on, and I'm not going to say PNM query. Well, I did. Protocol and metadata. So we need some basic information, what the schema of the table, what is this configuration, stuff like this. But we only fetch this small piece of the table that we actually need. When it then comes to materializing the data, nothing happens until you actually consume sort of this stream that we're serving. And there is this low-level kind of arrow stream interface. So we're actually passing this lazy pointer around, and somebody essentially starts to consume that, starts to pull it, and this is only when we actually start reading data from memory. Before, kind of nothing happens, and well, not nothing, but only very little happens. Yeah, and this is saying being lazy versus an eager compute model, which is say, I'll just fetch everything. And this is, interestingly enough, also kind of Spark, I think, also popularized sort of the lazy compute model a lot. You can do a lot with Spark, and it's immediate until you put like a collect statement or something like this in there, when actually the work starts to happen, right?
Yep.
Before, it's just planning and logical stuff, kind of.
Awesome.
Yeah, there's interesting work up the stack. Like if we use polars as an example, polars has a lot of laziness implemented into it as well. Laziness is also the async concurrency model of choice in Rust. But what that means is effectively we're only grabbing data when we're going to use it, and then in a lot of cases we're throwing it away. And so a polar script or a polar's query can go through, let's say, 10 gigabytes of memory, but only ever use 300 megabytes or 10 gigabytes of storage, but only ever use 300 megabytes of memory at a time, because it's only bringing the data that it needs to look at, doing whatever transformation processing, and then throwing it away, moving on. That also helps the sort of like high performance that you see with polar scripts or using Pyre or something like that, is we're lazily processing that data and not trying to keep everything in memory because we don't have enough memory to do that processing.
And just adding on top of that, certain optimizations only become possible in the lazy compute model. So if you imagine an eager polars frame or pandas or whatever, doesn't matter. You're like, okay, load this delta table. And then bam, you have all the data in memory. And then you say, okay, I want to filter this down with a where condition or whatever to this. And then you just immediately do that thing, right? So in a lazy model, what you can do is you can take this where clause and already apply it when you're reading the Parquet files and be much, much more selective. Whereas in an eager model, you don't know yet that this filtering operation will happen. So being lazy, just listening, what does the user want to do? And then saying, okay, you want to do this, and I'll do it that way in a much more optimized manner. Yeah. So let's see if we can get closer to actually talking about what this in kernel. So if you remember, the question is, how can we make open table formats more accessible, kind of, or how can we make them composable, not more accessible? And one idea that kind of comes out there is kind of express everything in a language that query engines are familiar with. And one core component that every query engine knows how to do is evaluate an expression. Because, well, if you're able to interpret SQL or using a data frame API,
the job. Like that's
yes,
what you do.
exactly. It's what you do, right? So if we look at this petition values, lazy sort of petition values is one feature that table formats have. We can express that as an expression written in SQL. Column mapping, we'll get into that, one of the more anticipated features in Delta RS, but part of Delta. Also, is fairly simple to express as an expression in SQL. Generated columns, and another feature, but it's nothing else than applying some function to some columns from the table and giving that thing a name. Check constraints, again, just move your expression in the where condition and enforce that it's Boolean, which is kind of then calling it a predicate, right? So building on this there is a kernel architecture. Finally getting to it, yeah.
No. I give you grief, but I think being in this community for the last 5 or 6 years, it's like simple things always look simple in hindsight. Getting to simplicity is the hardest thing to do. I had like one of the few computer science classes I ever took was with a developer named Bjarne Strustrup, who told me that making things simple is incredibly complex, which in hindsight was ironic coming from the creator of C++, but we'll leave that to the side. But building things simply is really, really quite difficult. And so this sort of realization that most of what we want to do can be expressed in these sort of logical expressions that we're already, as data people, very comfortable with, took quite a lot of development and exploration and prototyping. And so it is kind of like a drum roll, fireworks sort of thing to get to this point where we understand enough about the problem domain that we can articulate what the engine needs to do or what kernel needs to do as expressions that we're already familiar with, because we have everything that like query processing and engines have been doing for the last 40, 50 years, we can apply a lot of those learnings now that we see, oh, this problem is like that problem. We can now take a lot of the known best practices and bring them forward into kernel to make things better.
100%. And I mean, one of the things I also like to say sometimes is like the complexity doesn't go anywhere, right? The problem is still as complex as before. It's just somebody else kind of carrying the load and trying to hide that complexity while not constraining things. And that's kind of the hard part, right? It's easier to hide complexity if you take on the full load, but it's harder to hide complexity. And this is exactly kind of what we're looking at here, right? So a typical connector architecture is, and this is usually an engine has a specific, I don't know, I mean, Rust doesn't do inheritance, right? So it's not it's not a base class you're implementing. It's a trait, but yeah, in Java, I think there's definitely inheritance, but there is patterns that were used, and traditionally, you Data Fusion also has kind of this table provider trait that you need to implement if you want to kind of provide a table that can be referenced to in a SQL statement. And this is kind of, if it were easy, if we just kind of take that layer and say we're not caring about anything else, we'll just do everything within the integration, this is what it would look like. But this is where this blows up, right? This is where we essentially, if we remember before, where we're spanning the line between query engine and I/O. And this is kind of where the engine wants to kind of take back control and say, I'll do that, right? This pertains to credential management. This pertains to the representation of data or in memory, all of this goodness. So in the kernel architecture, very easy, we just move the integration into the engine rather than having any actual outside contact. So only the engine talks to kernel, and kernel only talks to the engine, and anything else that goes beyond this boundary, the system boundary, is engine responsibility. Looks simple enough. Let's dive really quickly through.
Very simple.
Just move the box over. I mean,
yeah, you just put that there.
how hard was that, right? So there is the table APIs, and then there is the engine APIs. The table APIs are what everybody knows very well, which is essentially what the user expresses, right? I want to read this table. I want to create a checkpoint, what have you.
Can you go to my favorite slide? Because I'm telling you, I think this is the best way to explain what you're saying.
We'll be there in just a second.
Okay. It's just my favorite slide.
All right, I'll jump through those really quickly. So what does it look like if we actually execute a statement? And here we assume that in this location, S3, my delta table, you'll find a delta table. So how does that work? Essentially, the planning starts, logical side in blue, physical side in orange. For those who don't follow the internals of query engines, this is kind of usually how it goes. You have a SQL query. That SQL query gets parsed into something logical. Then you can run an optimizer over the logical plan. And then you add additional metadata. I don't know, how do I actually open this URL? How do I don't know, what ordinal, like here you see project AB, here you see column 01. You move from, let's say, a name-based access to ordinal access, because that's much more efficient. You can optimize much more rather than looking up names and mapping this sort of stuff. But this is kind of where the translation between logical and physical happens. And the thing that we need to communicate here, or let's say the files to scan, is fairly easy to communicate because it's just URLs. But what we need to communicate is schemas and expressions. And this is where it gets interesting. So there is a couple of things that we need to communicate across the boundary between the engine and the kernel. The first thing is schemas. Table formats have a strong opinion about what data types are supported, what features they support. So all of this is kind of kernel natives. Kernel says, this is how I represent a schema, and you, engine, need to learn how to understand this. Yeah, then there is expressions. We could probably do an own talk about sort of the expression representation, and there were some people much smarter, at least than I, who designed all of this. And I'm not going to lie, it's not a trivial thing that came out of this, but it's a very powerful thing in that kernel knows how to handle certain expressions, but it allows the engine to define their own expressions. Different engines support different kinds of functions, and it would be infeasible for kernel to define.
Yeah, I mean, the closest parallel to what the kernel team has done here is, if you think of LLVM as an example, the compiler suite, a lot like LLVM has a front end, and then there's compiler backends. And so in between those two things, there's this intermediate language, the IL, and this expression predicate stuff is the intermediate language of Delta kernel. So we don't know, we can't, like LLVM can't possibly implement support for every compiler that exists or every programming language that exists, but there's a discrete set of this intermediate language that is supported. And so any application that's sitting on top needs to translate their magic functions into the expression language that kernel understands, and then kernel can do something useful with it. And so there's prior art for a lot of this sort of design across the computing industry, where you build a simpler intermediate layer and then express what you need to accomplish in those building blocks, and then you have the layer below use that expression to do something useful with, or those expressed intermediate steps. And so it does. You're right, Robert. It's like there are parts of this that seem wildly complex and crazy and complicated, and then there's some of it where it's like, oh, it's just like X equals Y. That's so simple, and it's like, well, neither of those things are 100% true.
Yes.
It's like picking the right subset to support is quite challenging. Like, how can we express as many of the concepts that exist in like Spark and Spark predicates? So, like, we didn't build a Spark SQL parser, right? But how do we express all of those things in as discrete of steps as possible that we can reuse across engines? And that's a non-trivial exercise.
Absolutely. And I think in this case, what's interesting, only the expression that kernel needs to, and remembering features are expressions, right? So only the expression that kernel needs to write are explicitly modeled. Anything else, the engine is free to pass to kernel. It can be used for file skipping and all of this, because kernel will never try to evaluate any of this. Well, it'll tell the engine to do that. But that's very interesting. But Scott, it seems like you were setting up to say something.
No, all I was saying was that all of this is leading up to the simplicity factor, right? It's if you want to make that expression select A, B from table happen, that feels simple. And then when you think about all of the stuff that's going on behind the scenes, and it's like on the fly compilation, everything else like that, like interpreting like that expression, like I'm like, people who've talked to me before about all of this stuff know that I'm from like essentially like the Java side of all of this. And Spark had like something called the expression encoder, which essentially was like how things became fast in like the Spark 2 days. And so for people who are coming in not like as Rust experts or kernel engine building experts, that's another kind of like example of things like within like the ecosystem that help make expressions happen. So back to you guys.
Awesome. So last but not least, we talked, let's go back. We talked about the data representation. Kernel doesn't know what data is. Sort of, it just gets this thing, this opaque blob, and the engine kind of controls how that is encoded, implemented. And the kernel just needs to visit this on a cell level. So there are some challenges with that. There was a nice interplay with Delta RS and Tyler kind of putting some load on the system that also helped the kernel team ultimately optimize kind of how this communication and this probing and all of this kind of stuff happens. But ultimately, the engine kernel doesn't know or care.
I want to do a quick solicitation for help. So some of the more interesting performance challenges that we've discovered and needed to fix have come from what I wish were more esoteric table types. We're talking about hundreds of columns wide or billions of transactions in the log. Like if you've got really interesting shaped Delta tables in your organization, grabbing newer builds of Delta kernel or Delta RS and just trying to like open the table, run things with those is actually very helpful to help us identify different, real world scenarios where some of our implementation is not where we want it to be. Is what tends to happen with projects like Delta RS is we have canned sets of data or someone generated a BS data set at some point, and then we test against that. And we're like, well, it works great on the BS data set. And then poor little Tyler goes along and brings that code into production with like really wild data that some data scientists put together. And things don't behave the way you expect them to. There's a really fun issue that Robert and I were starting to work through this morning where the Delta transaction log is huge, but the reason that it's huge is because somebody being me, included a column in the file statistics, but that column is an arbitrary string from a large language model input that could be, 100 bytes, or it could be 100 megabytes. And so the file stats in this Delta table are just completely screwy, and it causes problems. Like, yes, I shouldn't have made a table like that, but such that it is, I've got a table that looks like that, and we've got to figure out a way to make Delta RS and in turn Delta kernel RS work well with those sorts of like bizarro shapes of data that exist in the real world. So bring your bizarro data to the Delta project.
Please do. please do. Absolutely. All right. So we looked at expressionist schemas, and now Tyler finally will look into what actually happens when we invoke this sort of Delta scan, because this is where kernel does its planning. So imagine we're fully inside the blue box, we're inside the engine, and we're receiving a user query. And ultimately what we want to do is produce a response that we can serve back to the user. So what does that look like? A user query usually is kind of then split up, right? If you have select from, where, what have you. And we talked about optimizations earlier, right? The from table name usually gets translated to a physical location in the physical plan. So it's a URL. And we have a predicate, which is selecting column A and B, applying a where clause. All of these things ultimately translate into a predicate. So now, kernel, again, using the abstractions, and in this case, the lowest level abstraction that kernel has, which is just interacting with a file system. And there is two functions, list from and read bytes. We need to be very clear here. Read bytes is not used for Parquet or JSON reading or something. It's just we need this for parsing deletion vectors, what have you. And from this, we create our intermediary plan, because reading the log of a Delta table is actually nothing else than kind of just performing a query on an actual table. It's JSON and Parquet files that you're reading with a specific schema, and you may actually apply some predicates. So then we have that plan, which is essentially saying, read these JSON files, then read this Parquet file, and read these columns from that, right? So we have those functions, and if you're looking at something like Iceberg, we would also need like read avro, but the message is it's on the file format level, not on the bytes level, right? We're not using read bytes and then parsing the Parquet bytes or avro bytes or whatever ourselves, but we believe the engine is best at that. They know how to do this very efficiently. And then we have the expression evaluation, which is applying, we talked about the expression system, right? But there are certain operations we need to do on top of this data, and these operations are expressed as engine expressions. And then what we get back is the schema that we should expect to read from the files, and the schema that is kind of the logical physical schema is like column mapping and stuff like this contains this. We contain a list, we get a list of data files that we should read, and we get some more predicates, kind of in a sense of column mapping is the interesting part here. So the engine gives us where a greater 5, but a in the Parquet file is actually call blah 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 -1 GUID. And users usually don't like to type GUIDs by hand. So this internal translation of taking the logical predicate and translating it to a physical predicate in terms of the Parquet data is also kind of what this internal machinery does. And then the engine can go back and actually plan the execution, do the things. I need to read those files. I need to, yeah, and then serve the data back to the end user. Yeah.
Yes.
So, go ahead.
Oh no, this is awesome. I was going to say that I think if we want to kind of dive a little bit more into this without continuing further, then we'll have a little bit of time for questions as well, or we can just go straight to the end of the hour as well. So
I think if there are questions, it's great to have questions. Let me just mention one thing, because this is the gist of the very few slides that could come after this. But here, taking those predicates, which are essentially features and some other stuff, and rewiring Delta RS's internal scan. So we already have all the log replay done, but the current internal logic sort of stops right before we use this, what we see right here, to do the query planning. But once we consume this will also enable a column mapping, which people are excited about, and deletion vectors. And this is kind of the focus topic right now. Unfortunately, we do need to rewire some stuff. But the hope is that once this rewiring is done, kernel delivers on its promise, because all or most features are expressed in the same way in terms of expressions. But yeah, I think if we have questions, we can leave it at that.
Very challenging problem that Robert is alluding to. Much as I wish it were different, Delta RS contains a number of different code paths to accomplish similar things depending on what you're trying to do. And so the exercise that Robert, myself, Jan, Florian, and other contributors have been going through has been one of identifying where we kind of have technical debt that's accrued in Delta RS, and consolidating and trying to sort of narrow the places where we need to interact with a thing like kernel. Like there's a like IO subsystems, as an example, are sort of like everywhere, but narrowing that into where we're going through one place, so that when you do something like, so column mapping is a really interesting one, and it's taken Robert and I quite a while to get even as far as we've got. We map partitions correctly, which is fun, but other things don't map as well. Like if you think about every operation that Delta RS supports, like optimize, vacuum, table modifications, merges, upserts, writes, like all of those now need to become column mapping aware in order to, like, that. It's such a simple concept. It's like, it's this, but you call it that. It means everywhere you refer to this, you have to name it to that and make sure that it's always correct. And it seems so simple until you get into the code, and it's like, spaghetti arms going everywhere.
Yeah,
but it's promising work. I wish it were done, mostly because then I wouldn't have to work on it anymore. I just wish it were done. I wish we were there.
And I mean, just go ahead, Scott.
I was just going to say that I think, I mean, like with column mapping in general, for people who don't know what column mapping is, who haven't potentially seen the problems that occur with just straight Parquet, like if you are to move a column, like reorder columns, then you can't necessarily do that with traditional Parquet without essentially corrupting things. And so with that, it's like, if I had position 0, position 1, etc., like within like my true columns, if we think about like an ordinal offset in my Parquet, and then I'm like, oh, I'm going to reorder these things, I'm going to start writing in a different order now, that would be corrupt. But column mapping makes it so that's not corrupt, which saves everyone effort and goes back to the simplicity, that the concept we talked about, a couple slides back as well, where it's like, people shouldn't have to think about the problems, right? It's just, you can use the tooling, you can use these libraries to not have to suffer the same problems that they are solving, right? Anyways, yeah.
Yes, absolutely. I think if we have questions, we're happy to answer them now.
I think there was one that came up. I don't know what can be said, like in a public, I don't know, publicly about it, but like there was a question that was essentially like, because Databricks bought Iceberg, we're expecting that all this might also apply to Iceberg as well in the future. It's like, are we walking into a unified format? And like, what I can say based on like the conversations about like Iceberg spec for V4, there's a lot of talk about, it's like some of the things that made Delta Lake, great, like, relative file paths, things like that, are coming into the specification for Iceberg. So will there be something, in the future, will there be, this confluence of ideas? Yes. I think everything, essentially, everybody builds off of something else, right? It's a book called How Innovation Works, which talks about a lot of this stuff too, right? There's good patterns, and people continue to take those good patterns to do other things. But I can't answer for what the future will look like.
I wanna pick on part of that question, Scott.
Please do.
Databricks didn't buy Iceberg. Databricks doesn't own Delta Lake.
You said it.
As the resident open source flunky, it's important to say Iceberg is an Apache Software Foundation project, and part of the reason why we owe a debt of gratitude to Netflix for doing this is they donated it to the ASF to make sure that Iceberg remains a free and open interchange format. It's for the same reasons that Databricks originally spun out the Delta Lake project, which is under the Linux Foundation. I think these sort of vendor neutral meeting grounds where we have good governance and other things allow us to not let any one company sort of like dictate how the entire ecosystem works. But what you said is, from a technology standpoint, absolutely correct. There's been cross-pollination going on between Delta and Iceberg for 5 years. Like, there's a number of things that Iceberg incorporated into prior specs that came from Delta, and vice versa. I think one of the things that was highlighted there that I don't know what's correct, I hope there's more cross-pollination in this, however, is that the kernelization that we've been working on with Delta, I do think is a foundationally sound idea and worth bringing into Iceberg as well. I think it's valuable to have that demarcation line of, here's the thing that does the protocol specific stuff, and then we'll build on top of that. Iceberg, because it has similar sort of history as Delta, also has sort of a implementation sprawl. It's very similar problems. Like, it's like Mario and Luigi. Like, you can tell they're related, but they are different somewhat, right? But there's a lot that would have to be done with Iceberg to kernelize, so to speak. And if there were a unification of table formats, I don't know if that's good or bad. I think there is benefit into some differences, because we do have some different perspectives, and there's value in that diversity of viewpoint in the tabular formats that we have. But both are open source, both are open communities, both have good open governance. I think we should continue to cross-pollinate at our heart's content.
Awesome.
Yeah. And just adding on top of that, I think the point that we don't know, and no one company can decide any of this, is important. That being said, I think all the engineers and some of the contributors, they're not like Iceberg or Delta or Data Fusion or whatever contributors, but they need to deal with all of this, right? So if you're a format agnostic vendor and just want to integrate, you need to do all of that work. And ultimately, all of those folks don't really care about sort of the political layer that used to exist or used to be around this project. They just want this to work.
Yep.
And we've seen, as you said, like in V3, deletion vectors got included, and this was a community effort that deletion vectors look exactly the same between Delta and Iceberg, right? And I mean, there could have been where actually there was a couple of bytes difference between the two, which, I mean, would have been manageable. but the aim is to go for compatibility whenever you can, right? And there's a bunch of, again, Tyler said this already, powerful stuff and great ideas in each format, and let's see how much we can cross-pollinate. That being said, Delta has compatibility features, so at least those will have to be supported by Delta kernel. Like uniform is it's a Delta thing, right? So it needs to do this, and I hope that the community embraces. I'm advocating heavily for this kind of architecture in various projects.
Yep. Simplifying interoperability is always great. So
yeah,
I guess I'm like, with that, we're at time. So thank you everybody for coming on and spending, you know, your morning or your afternoon or your evening with us, or catching up whenever you watch this, like on the different socials and things like that. But thank you, Tyler. Thank you, Robert, for spending your time to,
Thanks for hanging out.
Yeah, thank you.
Thanks for allowing us to spend the time.